let's finish the other topics as soon as possible. Then we would like to introduce the quantization error, or the so-called quantization noise. Anyway, during quantization, actually, we discretize or quantize both the magnitude and the time. Both the magnitude and the time needs to be discrete instead of continuous. So from the very beginning, I already introduced such kind of very important concept for you. Yeah, to quantize the time, we call it sampling, and to quantize the amplitude, we call it quantization. Okay, yeah. So for noise, we have quite many types of noise. First of all, in addition to quantization error or quantization noise, we still have the others: random noise, interfering signals, error, hard noise, short noise, all of them. Yeah. Which one is important? Everyone is important, especially for high end. I mean high accuracy ADC or DAC. For noise or errors, you cannot eliminate anybody. To the most, you can reduce some of them, okay? But how? You need to have very careful design and focus on the side effect, try your very best to reduce to some kind of acceptable levels. That's it. Everything is imperfect, okay? Even the noise, you have no way to cancel it. Yeah, you can only reduce it, right? That is a very important concept. And why everyone is important? Because each one will have different impact on your enough effective number of bits. It is really important, all right? Yeah. So for quantization noise, that is what, if the input is sawtooth, right, or triangular, or periodical one, we don't care. You can see after quantization, so what is the error? It looks like this, right? I explained such kind of concept already. So the error amplitude actually is bounded, limited by positive, negative 0.5 LSB, right? So how, because we would like to, right now we would like to estimate SNR, okay? Yeah, the signal over noise. So we need to know how much energy. Instead of amplitude, we focus very much on energy. So how much energy for such kind of quantization noise? You have quite many ways to calculate, but since this is some kind of science, okay, instead of religion, so for all those ways, it will get the same result. Yeah, that is the beauty of science. You can verify it with different ways, but you always get the same result. Okay, so how to calculate such kind of energy? Because it is periodic, right? I mean, according to time, it is periodic. So for such root mean square, or square root, anyway, RMS value, actually, that is the equation. You learned it already from calculus or from statistics, anyway. You integrate for one cycle divided by one cycle for averaging, right? But we focus on energy. Energy means this one. Yeah, the square of your magnitude. Okay, so you integrate it and divide it by this, then the square root to get the RMS value. Okay, so do it. You can do it by yourself. And the other possibility is if you focus on the distribution of your magnitude, you can see, the magnitude of such kind of quantization error actually it uniformly distributes over negative to positive half errors. So, and distribute over such kind of period. Anyway, after calculation, piece of cake, do it by yourself. With some minutes, you will make the result. All right? So, this is the energy IMS for your noise. It equals the full magnitude, because from here to there, that is the full range, 1 LSV, right? Divided by the square root of 12. Okay, keep this in mind. All right, and then let's go for the other calculation, derivation. According to probability, you can see again, the magnitude of the signal, it is equally distributed over positive, negative, have LSV, right? So according to PDF, probability density function, okay, PDF, not the PDF reader, what kind of PDF file, no. That is from statistics. The magnitude actually is equally distributed from minus, so Q right now, sorry for that, because I hybrid different materials from different websites or professors, but I don't have time to help you correct the terms. Actually, the Q here is LSB, okay, the same, but sorry for that, I don't have time. I just copy and paste to let you know. Never mind in which way you derive it, you will get the same result. So according to PDF, you can see it is uniformly distributed. It means the probability is exactly the same from here to there, okay? But for probability, what is the overall probability? 100%, right? 100% means 1, right? So the width is Q, 1 LSV. So how about height? Because this by that should be 100%, I mean. So the height is 1 over Q. Okay, and it means what? You can derive, again, according to probability distribution function from the lower bound to upper bound. This is the magnitude and the probability. Okay, after such kind of integration, then we have the square root. Anyway, anyhow, you can see we get exactly the same thing. Okay, bingo. Yeah, but you will be curious because right now we need to focus not only on noise but also signal itself. Okay, so how much energy our input signal has? You can see for our signal, what is the distribution of your signal? Sawtooth. So it is also periodic. It is periodic, right? And from the minimum to the maximum. Wow, what? It looks like much similar to this. Okay? So yeah, you can do the same thing. You can do almost the same derivation for your signal, for your input signal. But according to the shape, they are almost the same, right? So yeah. Congratulations. After derivation, the same derivation, you get, wow, the range. I told you the full range from the minimum to the maximum divided by the same square root of 12. Okay? And then how to get the SNR? You divide the signal energy by noise energy, 12 yeah, both of the square root of 12 will be cancelled. You get this. Okay? Yeah, ideally, the reference voltage is divided by this. I mean, ideally, if nothing wrong. Okay? So for perfect ADC or deck anyway. Yeah. 1 LSB means the overall voltage, the full range voltage, divided by this 2 to nth power. Okay? That's it. So for such kind of signal to noise ratio, because usually it is really huge, if n is large enough, usually we express such kind of signal to noise ratio in dB. Okay, so we have this. Oh, because it is energy, we have 20. All right? If it is amplitude, we only have 10. All right? According to the definition of fundamental basic circuit theory. Yeah. Okay. Again, why 20? Because the. All right. So to the front. So you have 2 by 10. You got 20. Oh, I'm not your teacher for basic circuit theory, but I hope I can provide you the most help on earth. So finally, you have this. SNR equals 6.02 by n. Wow, it is totally different from what you guys learned in the past, because you need to my memory, okay? Yeah, why? What is the second term? We don't have any second term here, right? You need to be careful, because for all those equations you learned, you memorize, usually the input is sine wave. But right now, I am talking about the histogram test. The input is not a sine wave. It is the triangular or sawtooth wave. Sorry for that. Different input signal will have different energy. All right. So under such kind of situation, the result, the SNR in dB, you only get 6.02 n. But what is the problem? Again, for such kind of sawtooth wave, it is really hard to generate. I told you already, because the linearity needs to be 3 or 4 bits higher than your DAC or ADC, especially your ADC. It's really hard. For example, for sigma delta ADC more than 20 bits, what does it mean? Your linearity needs to be 24. I promise you, to generate a test wave with enough more than 24, I promise you, the design is even harder for 20 bits sigma delta ADC, even harder than that. Okay? So, usually, for high-end tests, humankind don't touch. Don't touch such kind of very linear, highly linear wave generation. No, that is too hard. What is the easiest waveform for humankind to generate? This one. And again, it is some kind of echo for my previous statement. I told you, I warned you, all those equations you memorized, you learned, basically based on this sine wave. Because sine wave is the easiest waveform humankind can generate, as close to perfect as possible, as close to the idea as possible. Okay? Why? Oh, because we have many kind of filtering circuit, low pass, band pass, any kind of pass, to make the output signal as perfect sine wave as possible. All right? So right now I would like to discuss, I would like to tell you how to test your ADC with sine wave input. Because that is the easiest way, perfect way humankind can generate. All right? So you put such kind the sine wave, and then, the green line is for sampling. And then the red line for what? Quantization. Two concepts. Okay? So what is the result? The blue one is for your real input. So what is quantization error? Oh, you subtract your blue line by the red lines. So finally, okay, blah, blah, blah. You get this. Oh, I need to tell you, all those waveforms are generated by MATLAB. So it is totally correct in theory. Okay? It is not measured. No, it is created by MATLAB. So no worries, it's perfect. I need to warn you. What? The error is much larger than 1 LSV if you have sine wave as the input. Okay, but the condition is what? The sampling speed compared to your input signal is not high enough. Okay, please keep this in mind. I'm not talking about for all the sine wave under any kind of circumstances you will get the quantization error should look like this. No. I am talking about the low frequency operation ADC. You will get high or low depends on your sampling frequency according to input frequency. Okay, so if your sampling frequency is not very high, I mean compared to your input signal, sorry for that, you will get something totally out of your imagination. Because I guess all of you, if you have some kind of idea, teacher always teach you the quantization error is within 1 LSV. Sorry for that. Under such kind of circumstances, it is not. It is far beyond. Okay. Wow. All right. And how to express such kind of error in mathematics? It is very messy. I cannot say it is impossible, but it is really hard and complicated. Since all of us, not only you, but even myself, we are engineers. I told you already, engineers are not some kind of ideologist. Yeah, we can tolerate errors. Okay? Only if the error is small enough. That's it. That is good enough. We are not ideologists. 我们不是极端分子，我们可以接受一点点的误差，只要误差够小。Anyway, anyhow, we wouldn't like to express the error with ideal equations. That is too messy. Maybe it is possible. Maybe. Okay. Maybe it is impossible. But we don't care because we are not mathematicians. We are engineers. So we are more than happy to get some kind of approximation or simulation or estimation, blah, blah, blah. Okay? But if you increase the sampling frequency, I mean compare to your original input frequency, you just raise the sampling frequency as high enough, then according to MATLAB simulation, what did you get? Again, that is the common idea. The quantization noise, again, is limited by 1 LSV. Positive, negative, half LSV, right? And also you can see, right now, the noise and the input is almost uncorrelated. All right? Let's go back. Oh, yeah, here. It is very important in theory. For the previous one, it is correlated with your input. Why? Because, this is the peak. from the noise, you can guess the input. This is the peak of your input. That is the bottom, the value of your input. Yeah, right? You can see. Right? Right? So they have some kind of relationship. We call it, in theory, correlation. If your noise is correlated with your input, I promise you, you will lose a lot of accuracy. All right? Because your input, some of your input will be passed to your noise. It doesn't make any sense. Signal over noise, some of the signal, will be involved in this term. It will increase the noise very much and reduce SNR substantially. It means your ENOP will be really, really poor. So we hope the quantization noise is uncorrelated with your input. Congratulations. If you increase the sampling frequency, the result look like they are not correlated. I am not talking about perfect uncorrelation. No. But roughly speaking, it's harder and harder. If you increase the frequency again and again, then it will become even harder for you to guess that is the value or the peak or any portion. All right. So again, you can see, roughly speaking, okay, you can see, the quantization noise, almost uniformly distributed between here and there, right? Right? So with the same derivation, you will get the same result. What is the noise energy? The full range magnitude divided by this. Okay? Got it? The same derivation. But to help you more, Professor Geiger would like to tell you some of the theory from statistics. From 统计学, statistics. Yeah, if the random, very important one, random variable uniformly distributed between A and B after derivation, blah, blah, blah. Oh, finally you will get this. The mean value is, A and B means the upper bound and lower bound. Okay, the average of your upper and lower bound. And then what is the standard deviation? Wow, bingo, see? The magic number. Square root of 12. Perfect. From the theory, statistics theory. Wow. Okay, so I told you already, they are randomly distributed between the upper and lower bound, right? So B here, A there. What is the average value? 0. And what is the energy, IMS energy? The difference. The difference divided by square root of 12. Wow. I'm really happy. Why? Because this magic number has a deep root in statistics. 根号12它有非常深的理由，有非常大的科学根据。我说从统计学来看。Okay, that's it. I'm really happy. So, what is the quantization noise with sine wave as the input? We still get the same thing. Okay? But the sine wave, as you learned already from your fundamental circuit theory, basic circuit theory. What is the IMS value of your sine wave? Well, this one. Okay, I don't need to derive because you learned already from your circuit theory. So this is the energy for your sine wave, input. And again, we derive the SNR by dividing this by that. Okay? The signal noise by quantization noise. Sorry, the signal energy by noise energy. Okay, you get that. And finally, in dB, you get not only this, but also that. Okay? The second term, 1.76, actually is according to sine wave. All right? If your input is not sine wave, sorry for that, not the same. All right? Again, this is a very good equation, a very good lesson and warning for you. Don't believe in everything you learn unless you fully understand the concept behind. Otherwise, for all the engineers, they focus on this, they focus on this. They only have this equation for the SNR. No, sorry for that. It's totally different. You need to consider all the conditions. Only if the conditions are the same, you can apply this. Otherwise, forget about it. Okay? Be smart. So, how to derive your E naught? Because if your input is a sine wave, then apply this one. Right? So, after measurement, you measure this. So the measure of the SNR is supposed to be less than the ideal value. So it will be decreased. So how about the E naught after measurement? So you move divided by this, get E naught. That is the most widely used. Okay, but please pay attention to this. If you would like to apply this definition for your E naught, you need to make sure your input is sine wave. All right? Sometimes if you go to CIC, maybe for low bit, maybe 8 bit, sometimes they don't use histogram. They use some kind of linear, we call it ramp, 斜坡. They use such kind of ramp function, ramp signal to test the linearity of your ADC. If you so you need to ask the engineers what kind of input you have, because they will only provide you this if you need to calculate the E naught by yourself. Sometimes they will offer you E naught directly, but usually they only provide you this. Okay, so you need to check. It is sine wave. You need to minus, you need to subtract 1.76, then divided by this. Okay, but if the input is not a sine wave, it is the ramp. Sorry for that. Or you need to be careful. You don't need to subtract this. Otherwise, you will lose almost 1/4 bit for your E naught. Okay, especially for academic papers, we compete with the others. 1/4 bits, 1/4 bit is still good enough to defeat all the others. Okay, so don't be fooled by the measurement. You are smart guys. You need to know all the equations, all the conditions to get the best result for yourself. But no cheating. Okay? Yeah. So again, be careful. If the measurement is for sine wave input, then you need to do it minus this one. If it is with ramp signal, then you don't need. You get this. Okay? Be smart. Be smart. Yeah. And why this guy? Yeah. Is so upset because never mind. You apply this for sine wave. You apply that for ramp signal. That is only the perfect situation. For the real measurement, again, I told you already, we cannot apply the signal for the full range. You need to reduce it. Okay? So it means what? The signal energy will be reduced. The E naught will also be reduced. That is the ugly truth. Okay? And don't ask me, how much percentage you can apply? 95%? 90% or 99%? I don't know. Why? Because it depends on many kind of parameters. For example, how good you can control the noise. If you can control the noise, minimize the noise, then you can increase, maybe you can apply 99% of the signal, right? I mean in magnitude. But on our campus, especially in this building, there are some kind of power electronics labs. Yeah. they always design something with, right now not kilowatts, no, that is too ridiculous for them. Tens or hundreds of kilowatts. Maybe in the future they will design something with megawatts. I have no idea, right? For tens of kilowatts, they have switching power supply, on off, with very high frequency. It generates a lot of noise. So on campus, especially in this building or in EE building, you need to be very, very careful because the noise is sky high. Okay? You had better go to CIC. But otherwise, even though your ADC does a very good performance, but you cannot measure it on campus. After measurement on campus, you always get very bad SNR. Why? Because the noise is sky high, according to the interference from power electronics labs. Maybe on campus you can go to some kind of wireless chamber, because it is totally shielded. You put your chips, your equipment inside. Oh, congratulations! You will get much better enough, hopefully. Anyway, you not only for such kind of full scale. See, forcing input to full scale is really stupid. Wow, I warned you already. And we have a lot of the other imperfect ideas, concept really set. Okay, so again, I would like to tell you, the real enough will be less. I cannot say much less. It depends on the environment for your test. Anyway, the major result will be less than this. Okay, the better environment, the closer to this or to that, depends on your input. Okay, so try your very best. Nothing is free. You need to pay a lot of money for that. Okay, then allow me to finish the quantization noise, yeah, or the enough related to sine wave input. This is the simulated result, and that is the SNR derived by this one, by this commonly used equation. Most of the engineers, students, or professors, they didn't pay any attention to the condition. They simply memorize this. That is ridiculous. Okay, and that is what I can help you to be a much better engineer than the others. Okay, that is the commonly used equation, and that is from the simulation in theory. You can see if the resolution. I need to warn you. That is the perfect condition. Okay, under perfect condition, but with accurate simulation or with the derivation from the equation, you can see 1 bit, 2 bit, 3 bit, blah, 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 blah. See? Ha! This one and that one. After 3 bits, for the much more accurate simulation, it gets 19 in dB. But from the equation, it gets 19.82. Not so bad, not so large in difference. And after that, for 4, wow, even smaller in difference, all the way to 10. You can see the difference between the accurate simulation in theory, okay, and the roughly estimation from the equation. Yeah, after 3 bits, no much in difference. And the difference becomes smaller and smaller and smaller for higher bit. So to play safe, if your ADC has more than 3 bits, then again, we are engineers. We are more than happy to accept the result here. It means we are more than happy to apply this definition for your ENAP. Okay, but less than 3, forget about it. Please go back to such kind of very complicated simulation to get a good enough for your ENAP. Okay, don't look down to such kind of condition. For gigahertz or tens of gigahertz operation, I think, yeah, 3 to 4 bits good enough. Okay, for many applications. Yeah. But right now, I think if you are only talking about gigahertz, I guess, yeah, for commercial use, yeah, 8 bits should be almost the minimum. But if you push it higher, then the higher frequency means lower bit, right? Then finally you will reach 4 or 3 bits for operation, even for real applications. Okay? Again, don't look down to them, especially for very high frequency operation. Yeah. And this is the idea I told you already. Never mind how large or how small you apply for your input, the quantization error is about the same. It's almost the same. So for smaller input magnitude, you only reduce the signal power. It is almost the same. So the SNR will be reduced. The ENAP will also be reduced. Yeah, anyway. Later I will have another very good example for you. Okay? But before that, whoa. Okay, this one. See? This is a very interesting example. For your daily life, that is the power of knowledge. Okay? After my explanation, you will know why. Even for humankind, they wouldn't like to do any kind of analog IC design. Even for IC designers, they never touch ADC, but the concept is still very important. This is a very good example for you and for the others. We have many kind of hi-fi audio, right? In our living room, not only in our living room, but also in your bedroom. Okay? Bedroom for what? Before sleeping. Sometimes humankind would like to listen to some kind of soft music, light music, not hard pops, not rocks. Okay? To calm down yourself for better sleeping anyway. But what kind of audio equipment, audio machine you need to buy? In the AV house or in the living room, usually, we watch the movie, we watch many kind of animal videos, blah, blah, blah. Well, we need hi-fi. Yeah. We need hi-fi audio, right? So, for example, you buy a very good, 14 bits actually is not very good, but yeah, allow me to show this as a good example. For example, you have such kind of 14-bit audio amplifier, okay? It can provide for the maximum 100 watts. Yeah, that is the common case. Hundreds of watts for indoor use. For outdoors, usually, yeah, 3 or 4 orders, okay? Because they need to have very loud speaker to please tens of thousands of people in the same place. Yeah, anyway, yeah. So that is we call rating, the maximum spec from your device. But before sleeping, right? You cannot turn the volume to the maximum. Your neighbors knock your door or call the policeman to bother you, right? So you need to turn the volume down. For example, the output power reduced from the peak to this one. Well, only 50 milliwatts. So before sleeping, you can enjoy the music, right? Anyway, I told you already, never mind how large or how small the input is, the quantization noise is about the same. The interference, the hot noise, short noise, any kind of noise, never say, hey, this is really a pity. Oh, you have very small input, so I would like to reduce myself. Forget about it. No way. Okay, the noise, the interference is about the same. So, by reducing input energy from 100 watts to 50 milliwatts, the signal energy is reduced by 33 dB. But I told you already, the noise energy is almost the same, right? So the measure of the SNR will also reduced by 33 dB. So after calculation, yeah, 33 by, because it's the same number here, the same number there. Oh, you reduce it from the ideal value. 90.6 dB is for this, okay? But right now, for that, you only get, you reduce the magnitude of the input from 90 to 50 something. Ah, sorry for that. You only get less than 10 bits in accuracy, okay? So what is the lesson you can learn? For your bedroom, you don't need to buy any kind of luxury AV device. Yeah, you just buy some portable device, maybe with hundreds of NT dollars each. Good enough. Okay. For your living room or AV room, usually this should be better than 20 bits. The enough should be better than 20 bits. But for your bedroom, anyway, I guess maybe 12 to 14 bits good enough. Don't waste your money for nothing. Okay? Okay? Yeah. This is some kind of brief summary for enough. For the resolution itself, I told you already, it doesn't deserve your attention because it means nothing. We focus very much on the measured value instead of the the value you claim. 你宣告的没什么屁用哈，量测的才是王道。So if you have analog-based one, yeah, you have this, you have that, okay. For quantization noise, yeah, for triangular or ramp input, you have this enough. For sine wave, you have that enough. Wow, we have the other enough, but till now, I show you 1, 2, 3, 4, 5. Already, we have 5 definitions, but more than that. Okay? So what lesson you can learn from this slide? You need to be smart. You need to know the overall condition, then choose the correct one for your measurement. Yeah, to get the correct enough for yourself, for your customers. No cheating. Okay? And then we go for, that is, we can go for the other spectral characteristics. In spectrum, I mean, 频谱的. Right? So for such kind of, for spectrum, usually we focus on AC. And for all that, usually they are DC or close to DC. So sometimes we call they somehow DC or pseudo DC. Pseudo. Later you will see it. Okay? For such kind of analog DNL, to check how much linearity your data converter has, that is some kind of DC parameter. Yeah, anyway, you have this, you have that. For example, which one is better? For definition, they are the same. I mean, for analog definition, they are exactly the same. But if you have such kind of deck for your audio device here, here, and there, tell me which one is better. If you have a very cheap, portable AV device, audio device, which deck you would like to have for your daily life? For specification, I mean for the definition of INL, they are exactly the same. But which one is better for you to listen to the music? Huh? Which one? Which one? Which one? Which one? No idea? No idea? This one. Why? Again, usually we don't apply such kind of full range input or output. Okay? So if you turn the volume down a little bit, you can enjoy the linearity here. It is perfect here. It's perfect linear here, right? Right? If you don't touch the other one, if you touch this one, you will get some kind of distortion. Your sound wave will be distorted. with distortion. But if you reduce the output, the volume of your output, you can enjoy it. Perfect. Okay, and how about this one? Wow. Wow. Yeah, the second best is this. The third and the worst is that. You have a lot of distortions. Jumps. Wow, it doesn't make any sense for your output, right? But by definition, they are the same. So for our daily lives, usually we don't enjoy any DC output. We enjoy AC output. Your audio is usually AC signals. Okay, IUL, kakikukiko, right? They have many kind of, measure the output of the microphone. You will see something like that. Okay, so for our daily lives, usually AC is more important than DC. And it means what? With INL or DNL, it doesn't make too much sense. We had better have another definitions to check the AC performance of your data converters. All right. So, yeah. Usually, for circuit theory, to check the AC performance, usually we have distortion. Okay? And we focus on such kind of spectral performance. Spectral means something related to spectrum. 频谱的 ，OK， spectrum 是频谱，这个是频谱的。Anyway, for INL, DNL, blah blah blah, all of them, they focus on DC or very low frequency. So sometimes we call it pseudo static. Yeah, pseudo means virtual. All right, approximately. So you can see. For many of them, from DC to some frequency, it looks about the same. So we call it pseudo-static. Here, static means DC, right? Right? But beyond DC, the performance is about the same. And after some frequency, wow, it goes down. That is the usual case. In this region, we call it pseudo-static. All right, then we go further. How to do such kind of spectral analysis are usually Fourier transform, Taylor series expansion. Taylor 展开式 blah blah blah. Okay, as you like. I don't care. I don't mind. Fourier or Taylor. Okay, they are good guys. Yeah, for mathematics. For our system, linear system or nonlinear system, usually you can apply some kind of sine wave for your input and measure your output. Then, in spectrum, you can check the distortion. Okay? Yeah, that is the usual case in the past. This is some kind of Taylor series expansion. I don't care. After you have such kind of spectral analysis, never mind through Taylor series expansion or Fourier transform. Yeah, anyway, yeah, you have something like that. Because you have distortion. I told you already, if the system is totally linear, then sine wave input, sine wave output, perfect. It is also another sine wave with the same frequency, but different magnitude and different phase delay. That's it. Okay? If it is perfect linear, you still introduce some kind of delay and some kind of maybe attenuation. Okay? So the magnitude, the phase will be changed. But if it is linear, I promise you, sine wave input, sine wave output. Bingo. For sine wave output, you have only this one. One nice spectrum. You don't have the others. But sadly enough, if it is nonlinear, it means what? The output will not be perfect sine wave. Okay? But according to what you learned from linear system or circuit theory, it is still periodic with the same period of your input. Because your input is periodic, right? Your output, you mean here to there, here also to there, the same position. Okay? Never mind what kind of wave you have for the output. Yeah. The same one input will get the same output. That is the idea. So you are periodic. I will also be periodic. Again, the same input will get the same output. The same input will get the same output. That's it. Okay? Okay? So the output will have the same period as the input, but if it is nonlinear, then you will have some kind of distortion. Distortion according to Taylor series expansion. Haha. You have the same period, so you get the same fundamental frequency. 基频是一样的. Okay, but you have distortion, then you have many kind of harmonics, higher order harmonics from the second to the third all the way. Okay? Yeah. So, according to Taylor series expansion. Yeah. If it is perfect, you have only one. I told you already. Yeah. But sorry for that. Nothing is perfect, so you have such kind of harmonics. And usually, the second or the third is the largest. That is the usual case. I am not talking about it is always like that. No, no. But usually, the second or third. How to cancel the second differential output? Then, the third will dominate your performance. Okay? And usually, the second is larger than the third. Oh, congratulations. You can enhance your SNR. Okay? Oh, the other one is band limited. It means what? After some frequency, nothing existed. That is the definition for band limited. But that is not the usual case. Usual case is it decays all the way to very high frequency. That's it. Okay. So again, allow me to show you some kind of distortion analysis for circuit theory. First of all, THD, total harmonic distortion. Yeah. What is you would like to have? The first, right? The fundamental frequency. And what you hate, all the other harmonics. So the energy for the first and others. We compare this to that. Okay? So for ideal case, we don't have that. We only have this. The THD should be 0. That is the ideal case. But for practice one, sorry for that, you have some harmonics. Okay? And then we can go for SFDR. What is SFDR? This one. Spurious free dynamic range. Yeah, so it means, your signal, the difference between your signal and the highest harmonic. And I told you already, usually the second or the third. You can reduce it, the second, by differential operation. So your circuit only needs to focus how to cancel it to reduce it, because all the others are much smaller, usually are much smaller than the second and the third. Okay. Anyhow, that is the definition for the so-called SFDR. Okay. Yeah. A spectral analysis. That is in theory. Oh, forget about it. And then we go for SNR SINET. SNR. What is the popular definition for signal to noise ratio? Because nothing is perfect. So the signal energy here, and how about the noise? Not only quantization noise. Oh, you need to be very careful. For the equation, you have SNR equals n plus okay. It only focuses on quantization noise. All right. But for practical case, we have not only quantization noise, we have interference, we have random noise. So for practical situation, you need to take care of all of them. You need to pay attention to all of them. So for such kind of SNR, usually humankind, suppose that is some kind of experience. Okay? Yeah. 经验值 experimental value. Okay? So anyway, suppose this one are all about the same with that. Okay? So what does it mean? Noise by this. And dB, 3 dB. Okay? Wow! All right? So, how to, oh, no, sorry, not, if enough, like, right? But for practical situation, these are, so you have extra term. Extra term means almost 3, right? So, you get this by almost 3 dB, less than 3 dB. So the enough for practical consent, okay, SNR for real consent. These are for real, for practical consent. Okay, it should look like that. Okay, that is the difference. Ideally, you learn this equation, right? After measurement, you need to subtract this one, then divide it by to get this one. But for practical consent, I mean according to R, pay attention to the subscript. That is some kind of trick the vendors will always like to play. Okay? With R, it means what? After measurement, nothing is perfect. So they don't subtract. After measurement, they don't subtract this. No. They add that. Okay? So that is real life. Do they cheat us? No. In practice, they can apply this definition. All right? That is also a standard definition for the industry. So you need to be smart. As a buyer, as a consumer, you need to pay attention to this. With R, it means after measurement, they will automatically plus this one. So plus this one and minus that one means what? The difference in enough is half bit. So for the vendor, for the designer, to increase enough by half bit is really hard. So they can play the tricks with this definition and that definition for nothing. They can get extra half LSB. Wow! Half bit, not SB, half bit. Wow. But again, I told you already, that is not cheating. That is only tricking. They play tricks. 他们玩把戏，但是他没有欺骗你。Okay, that is difference. So it is legal. If you, after you buy something with a much higher price than you expected, right? You can sue them, but you will fail. Why? Because you don't pay attention to R. With R or not, help bit in enough for difference. Okay? And then we go for SINET. SINET, signal to noise and distortion ratio. Okay, distortion. Distortion means this. All the harmonics will be integrated into the equation. So finally, and they supposed to be this one and that one, and all three terms are about the same. It means what? Right? From square root of 2 to be square root of 3, blah, blah, blah. So, wow. That is the difference. So, after measurement, if you have enough according to SINET instead of SNR, and for real consent, practical consent, you can see after measurement, I can 8, 3, dB more, and then divided by 6. Wow! You can see from minus this one to plus that one. For ENAP, it's already 3/4 bit. Wow. See? Almost 1 bit. Without any effort. Only play tricks. Yeah. They can get more money for almost 1 extra bit. It doesn't make any sense, right? So, again, to be smart, I told you already, you may not design any ADC or DAC in your own future, but you need to know all the definitions. Otherwise, you lose quite much money for this. So, again, the second enough summary. Oh, we have this, and right now, we add extra 2. Do we finish all the definition for ENAP? No. They are the others. So, get a warning from this. Be smart. Don't be cheated. Don't be tricked. Okay? Yeah. It is legal. Okay? If you shoot them, you pay attention to this. Okay? Yeah. Without R, we have the same equations. With R, you can see totally different. Okay? Then, what is summary? Be smart. That is what I need to tell you. And the others, we call it a sparkle, meta stability. For ADC, you always need to compare your input to the quantization levels. Your input is higher or lower, right? We need a comparator. But if the input is too close to your quantization level, sometimes the comparator will generate output different from 0 or 1. Okay? So what is the result? Nonsense. And the ADC output will become very strange. Under such kind of condition, we call it meta stability, 假稳态. That is error. That is incorrect. Okay? Anyway, for such kind of meta stability, sometimes we call it sparkle, flyer, rabbit. It has many kind of definitions. For commercial ADC, how can I say? Usually they don't mention this. Why? Because it is very hard to measure. Because it happens with very low probability. But I promise you, it exists. Never mind how hard you try. Nobody will promise you no meta stability. Forget about it. It is proved already. Never mind how hard you try, how you improve, how you modify your circuit. In theory, there must be probability for meta stability. Okay? That's it. Yeah. But it is really hard to measure, right? So usually, even for TI, for analog device, they don't mention this. Forget about it. But it, okay? Oh, yeah. Okay. Sparkle, rabbits, flyers, as I told you, many kind of terms. Yeah. For this, for analysis, forget about it. Yeah. Anyway, we are engineers. We are not mathematics. Other terminologies, data throughput. Yeah, how many samples? It means how many you can generate from your data converters. That is throughput. Okay, so you can see, you can guess. The higher speed, the more throughput. Yeah, roughly. And then latency. I think I told you already. From your input, how much time you need to wait for the output to be generated. Okay, that is the thing. Not only for data converters, for your mobile phone, for your routers, anything. Okay, we have the same definition for latency. Yeah. Anyway, yeah. Finally, I would like to conclude the difference between designers, between the sellers and the buyers, 买方跟卖方. Yeah, because we have many kind of definition. you need to be very careful. Okay, yeah. Allow me to show you analog device. The top analog IC design company on earth, the best is TI. Okay, AD may be the second, and the others linear technology, national semiconductor, yeah, blah blah blah. This is some kind of data sheet, block diagram, no detailed circuit, yeah, according to copy. And then this is some kind of specifications. Be smart. That is the usual rule. They only need to measure the worst case. So, for example, for INL, typical value, wow, looks not bad, right? But they measure this. If you buy the chip from AD and measure the result, wow, it is not this. Oh, it is positive, negative 4.5. You go to the court to sue AD, you fail. Why? Because they only promise you the worst case. Okay? It's really upset. Again, it is legal. It is legal. So that is some kind of tricks between the sellers and the buyers. Be smart. For SNR, for something like that. Oh, very good. Forget about it. They only promise you the worst case. Not for that. Sometimes by imagination. Sometimes according to their experience. That's it. Okay? Then allow me to show you the hard work by Professor Geiger or his students. Yeah, they have for the more than 10 years ago. Anyway, from TI, the best analog IC design company, ADI, maybe the second analog device. Yeah, from nominally the resolution 10 bits to 14 bits. Yeah, this is some kind of the summary. For the shaded one, okay, they are not measured. Oh, this is real upset. Why? You can see you need to face the consequence. For example, 80 clamp for enough for quantization noise, they claim 12 bits for enough, but it is not measured. Okay? The measured value here, according to INL, oh, it is only 10.8. There is a big difference between the unmeasured one and the measured one. Right? Even worse. Okay? But please pay attention. How many bits they claim from the beginning? Oh, 14 bits. 14 bits ADC after measurement. They can only promise you 10.8 in accuracy. Wow. That is the ugly truth. But again, I need to warn you, it is legal instead of illegal. Be smart. You need to pay, wow. Oh, more than $50 for each chip. But you only get 10.8 bit in accuracy. Oh, so you can go back to this one. Almost the same. Right? Blah, blah, blah. Okay, be smart. Be smart. So if you are smart, even you don't design ADC, according to this, you can argue, hey, no. 10.8 bits. So I can cut the price from 51 to 31. Okay, be smart. You can help yourself, your company, save a lot of money. Okay? That is what I can help. To wash your brains, to debug your brains, to get good enough understanding before your design.